Hello everyone. In this segment, we would like to pose a few questions about AlphaZero-like schemes. Along the way, we will also introduce a few techniques we have developed and present a few results. These results, however, should be viewed as preliminary because these results only serve to spawn new questions, and those new questions all remain open. Therefore, they should be considered as a sort of elucidation of the real content of the questions we ask. Let's begin by taking stock of the situation so far. From earlier segment on the history of computer Go, we have seen that AlphaGo has clearly outstripped humans in playing strength. From published records, we see that AlphaZero is even stronger than AlphaGo. Now, the ideas behind AlphaZero, which is capable of creating a playing agent entirely from self-training without any human knowledge input, have been very, very attractive to researchers. Consequently, there have been numerous emulators of AlphaZero. Algorithms created by these emulators will be called AlphaZero-like algorithms, and many of those have also reached superhuman levels of play. Now, rather than joining the crowd and try to create another version of the same, we have taken a step back and asked instead a few very naive but at the same time also very natural questions. First, how close are AlphaZero-like algorithms to perfection? And second, if they still have some room to improve, do humans have a role to play? And we have developed some techniques in order to probe these questions, but before we get into that, let's try to understand our own questions better by asking an even more naive question. Namely, when we talk about playing perfectly, what does that even mean? Let's think about that. If I play well, then I should be able to win. So therefore, a perfect play must be the best play and therefore the winningest play, right? Of course, that's right. But you know what I will ask next, don't you? Namely, now I want to know, what is the winningest play? What is the meaning of that? Let me begin by presenting you with two familiar diagrams. You have seen them before, in fact, from the previous segment on the architecture of AlphaZero-like schemes. On the left, you see the playing agent is very confident about what the next move should be, namely the point A3. It's a white's move, by the way, so the playing agent I'm referring to is playing white. On the right-hand side, you will see that almost all of the legal intersections white can play carries about the same percentage. Even though C6 is chosen, look how close it is to the neighboring points. Now what happens is that when the playing agent thinks it's winning, what happens on the left-hand side diagram often happens. The playing agent is very confident. When the playing agent thinks it's losing, then you often see what is on the right-hand side diagram. So now, the funny thing is, if you compare only the stones on the diagrams, you find that the game position is actually the same. So how is it possible that the white is both winning and losing at the same time? And the next question is, to play the winningest move, does white play the same play, make the same play anyhow? So now we come to the tale of two perceptions, so to speak. Why is there difference of perception? This is actually created by Comey settings. On the left-hand side, well, the playing agent is trained on a 9.5 point Comey. And when that is the case, white perceives that it's winning. And because of that, it chooses a conservative play, which is the play 1 that you see on the left-hand side diagram. The playing agent that is playing the right-hand side game is trained on an 8.5 point Comey. And when that is the case, white thinks that it's actually losing. So therefore, it has chosen to play an aggressive play. So therefore, AlphaZero or an AlphaZero-like algorithm is a little bit like a chameleon. The reaction to the situation depends on the environment, so to speak. And in both cases, they try to play the winningest play, but they turn out to be different. In more human terms, we can say that AlphaZero has got personality. But that's a little bit funny, since an AlphaZero-like algorithm is supposed to be trained from a blank slate, a tabula rasa. How can it have an inborn disposition anyhow? Well, but that is what we have observed. Now let's analyze the plays themselves. It turns out to be the case that the play number 1 that you see here on the diagram is an optimal play. Now, by definition, an optimal play is a play that either maximizes the winning margin or minimizes the losing margin. Now, how do you know that the winning or losing margins are maximized or minimized? It depends on all of the subsequent plays also being optimal. So therefore, the definition of an optimal play is kind of a result from a reverse induction. But if you think about it, such a definition does make sense. And in any case, in the particular situation you see here, white 1 is an optimal play in the sense that it maximizes the winning margin, which, by the way, is half a point. However, personality is not equivalent to optimality, unfortunately, because the play you see here, the aggressive play that AlphaZero chooses to play when it perceives itself to be losing, is in fact suboptimal. And in this particular case, it means that in fact, if black knows how to answer correctly, white will lose even more than half a point. So therefore, the AlphaZero-like agent is a strategic player, not an optimal player. And indeed, it is choosing the winningest move every time. And this is actually dictated by the win rate, which you have heard from the architecture segment. But it's not optimal in the sense that every move is either maximizing the winning margin or minimizing the losing margin. Okay, we have quite a few examples of this kind, and in this segment we can only present 1 or 2 of them. But the technique that we have developed so as to be able to uncover situations like this, we have dubbed targeted evaluation. Now I want to present the other side of the same coin as well. In the previous example, AlphaZero or an AlphaZero-like algorithm chose to play the optimal play when it thinks it's winning, but it chooses an overly aggressive suboptimal play when it's losing. But AlphaZero can make suboptimal play in the other direction as well. In other words, when it thinks it's winning, sometimes it chooses to play suboptimally just to guarantee an easy win. In other words, it wants to avoid complications. And yet when it thinks it may be losing, then it plays the optimal play to eke out a win anyhow. And this is the situation you see here. On the left-hand side, AlphaZero or our AlphaZero-like agent chooses a very simple play, the play number 1 you see here on the left. And in fact, it's so simple that after black plays the next move, the whole game is finished. But because of the Comey setting, white wins, and therefore white is content. On the right-hand side, however, because the Comey setting is more severe, white would lose if it chose to play like what it did on the left. So therefore, you see, it had no trouble to follow a much more complicated sequence of play so as to win the game by half a point. Well, targeted evaluation, the technique that we have developed to show the previous examples, also allows us to observe other interesting phenomena as well. It turns out that in certain game situations, even optimal plays are non-unique. Now, when you think about it, this is not really that surprising. We have seen that Go is an extremely complex game, and complex problems sometimes have complex answers. So in this particular situation that you see on the diagram, the points A, B, and C all turn out to be optimal. In other words, they maximize the winning margin or minimizes the losing margin depending on the Comey setting. So therefore, if you think that an AlphaZero-like program is going to be totally random and impartial, then with probability 1/3, it should choose A, B, and C with equal frequency. But that turned out not to be the case. I have told you that we have trained several agents under different kinds of situations, conditions. Now, one of our agents prefers to play A, and it plays at A roughly 90% of the time. And another agent of ours prefers C, and it plays C basically 100% of the time. And none of the agents likes B. Now that seems like a habit that the playing agent has developed. But why? A machine is not supposed to have any kind of willpower or habit and things like that. Well, we have some ideas, but this is not the point to get too far into this problem. And in any case, we have not really formed our final conclusion yet. But this is the phenomenon that we observe. So, in order to summarize the situations so far, I am going to present these conclusions. Some of those conclusions are a little startling, in fact. First, although an AlphaZero-like algorithm is trained without human knowledge, its win-rate-dominated decision-making process causes it to display some human-like qualities, such as taking risks when behind and playing safe when ahead. And that was seen in the first couple of examples. Now, because of that, an AlphaZero-like algorithm can actually impede the display of optimal plays. And what I mean by that is that at some point, the playing agent may perceive itself to be losing and therefore chooses to deviate from the optimal line. Or the playing agent might think that it's winning comfortably and thereby also deviating from the optimal line in order to protect the win. And on top of that, there is also the possibility that an AlphaZero-like algorithm simply does not know where the optimal play is. So I have added here the clause, even when it is capable of making optimal plays, an AlphaZero-like algorithm may nevertheless impede the display of optimal lines. So now, because AlphaZero-like algorithms are presumably superhuman in playing strength, we need to know that this is happening before we can discover where the deficiencies are. And the third conclusion is, it also has a tendency to settle on favorite plays, as we have seen in the third example. And that is suggestive of what the psychologists and philosophers have called volition. Now, the machine is not supposed to have volition, and yet we have observed phenomena of this kind. And it is definitely deserving of further investigation. Well, now that we know that AlphaZero-like algorithms have some room for improvement, then the new questions are almost endless. And again, like I said at the beginning, they were spawned by the few results that we have been able to show in a rather definitive sense. So I'll ask three brief questions. First, can we help such algorithms to become more robust, to become more versatile, and to be more capable of dealing with situations the algorithm has not encountered in its self-training process? Second, can we help such algorithms to find globally optimal solutions? By globally optimal, I mean I want every play in the sequence from the beginning to the end to be optimal. And because optimality is defined by a sort of reverse induction, this is a tall order, because before you place the first stone, you already need to know how the game is going to end, all the way down the road. But on the other hand, it is a logical quest that we should have. It is actually of foundational importance. So the question is, can we help the algorithm to find such globally optimal solutions? And the third question plays into both of the questions we have asked so far, actually. Can we help such algorithms find multiple optimal solutions? Well, the algorithm needs to be robust. It needs to have more complete game knowledge in some sense. And the algorithm needs to be capable of finding globally optimal solutions. before we can count on it to find all of the optimal solutions. Well, we have developed techniques to deal with such situations as well, or at least to try to handle situations like these. And some of them were called targeted training and parallel games. But perhaps we'll wait for another chance to discuss these further. We also have some positive results to present. For the moment, let me make some final remarks concerning the scope and the intention of our project. Because you see, so far our project has been carried out on the 7x7 board, which is far smaller than the standard 19x19 board. Now, using the 7x7 board allowed us to be able to carry out our experiments more cheaply, and to also demonstrate that there indeed is something to look into here. But naturally, now that we know that there are things to be discovered, we would like to enlarge the board so as to be able to look at situations that resembles more the real game. However, once the board is enlarged, we enter virgin territory. And this is because humans have no idea what the optimal plays are like on boards as small as the 9x9 board. And in fact, there have been tournaments staged among professional Go players on the 9x9 board. So all of the discoveries we will be making will be new to humans. But most important, if we think about it, all of the questions we have asked are actually of foundational nature. If we make obvious modifications, well, these questions will be relevant for other algorithms that involve convolutional neural network as well. And we would like to say that this is the real intention behind our project. Thank you very much.